have this last presentation before the break. Then we will have 30 minutes break from 3:30 to 4, and then we expect you to come back to finish a couple of other presentations and the panel. Thank you.
Thanks a lot. My name is Ralf Kontner. I work for Siemens. I'm the head of the microgrid business within Siemens, and today I want to talk about what we see as the opportunities at the grid edge, or in my own words, the changing role of microgrids in the energy system of the future. The energy system has changed fundamentally in the last 5 years. We all know that. But if I should summarize the recent discussions or all the presentations I've seen on this summit so far is, well, the change in the last 5 years will be nothing compared to the change ahead of us. So what are some of the themes that we see already on the horizon to paint the picture of what the energy system of the future will look like? What we see is that, or what we see is that the energy consumption, or the electricity consumption, will double by 2050. And 50% of the doubled electricity consumption of that energy will actually be produced by renewable generation. This means that the formerly separated systems of energy supply and energy consumption or demand merges together. We will no longer have a traditional energy supply network business, generation business, and the buildings business, the infrastructure business. But what we see is that supply and demand will get closer and closer together, and will actually need to be managed together and optimized together in order to manage this increasing decentralization and this fast increase of complexity of the energy system. Some people call this merging of supply and demand the grid edge. So this is where we see most of the change happening, actually where networks meet consumption in buildings, in infrastructure. A second key theme that we see is that 7 out of 10 inhabitants of this planet will be living in cities. 7 out of 10, that's massive. So in other words, to manage climate change, to manage our energy system, the fight for this planet will be decided in cities. Moreover, what we see is that 1/3 of this energy in cities is actually going to be consumed by buildings. And today, half of this energy in buildings that gets consumed by buildings is wasted, is dissipated into waste heat, into waste electricity. So right at the buildings, at the grid edge, where energy is, where supply and demand meet, we call this the grid edge. We see certain technologies and certain business fields emerging. In this grid edge area, we see the majority of activities, investment actually happening in three business fields. The first one is distributed generation. That means power generated at or near the point of consumption. Could be generated in buildings or in industrial districts or at airports or parts of the infrastructure. The second key element we see is energy storage. Energy storage means battery storage, that's a big topic, but also thermal storage, all the different forms of energy storage that are either part of buildings, part of the energy system, or somewhere in between. And the third element is, I would say, e-mobility infrastructure, or moreover, the increased installation of significant controllable loads. That could be heat pumps or electric mobility. Those loads need to be integrated in the system in a smart way. And what we see happening is our energy system has transformed from a system of thousands of assets into millions of assets. That's where we are today. And with this increase of complexity, we see that actually we're going from the millions to the billions of assets. What we need to do is, we need to manage this complexity, this increasing complexity of connected assets, grid edge devices, of buildings, of consumers, of charging infrastructure. They need to be managed in a very different way than we managed our energy system in the past. So in generic terms, we have to harness the power of data. We have to collect the data, we have to analyze the data, we have to apply machine learning, AI algorithms to manage how those assets consume energy, produce energy, exchange energy, and manage flexibility and manage the KPIs of the network. And we believe with this increasing ability to manage and harness the value of data, we can help the energy system in all aspects. We can plan and develop better, we can build better, and most importantly, we can operate better. Most of our energy assets are installed and then running for the next 20 to 30 years, and the requirements and the patterns how these assets are going to be operated changes quite significantly. So the ability to manage the data, to tweak how we operate and how we use the assets is going to be crucial to derive the value from those assets, either through reducing cost, through reducing operating cost, or driving more value, i.e. generating more revenue or creating more customer value from those assets. I want to invite you to follow me and imagine the possibilities we have with that. What I'm going to bring is a couple of case studies that we see being implemented today already, and I think they can help to paint a picture of what's going to be possible and what the elements of the energy system of the future will look like. The first case study I brought is from a microgrid project in Italy. The situation is the customer has a white-collar office building, medium-sized, 30 kilowatts of load, that's medium-sized, and he wants to install the charging infrastructure for 5 electric vehicles, so a moderate number. Already the charging infrastructure for the 5 electric vehicle exceeds the local grid capacity and exceeds the local load of this office building by a factor of 5. So in order to realize that, the traditional way would be to dig up roads, to place new cables, to upgrade the substation transformers. That takes time and is expensive. Also, the customer wants to make sure that he can use the vehicles when he needs them. Those are company cars. They need to be charged. They can't be just load managed when there's no grid capacity available. He needs to rely on having those cars charged and available. The solution that we have built together with a customer is a local microgrid. So we've installed a car park PV, a small battery storage, and then we have installed a local controller, a microgrid controller. We've also connected the charging infrastructure to our smart charging e-cooperation center. And what we do is, on the one hand, we optimize the energy supply through the local generation, the battery storage. We make sure that the charging requests of the cars, the scheduling, can always be guaranteed that the cars are charged and available when the customer needs it. We make sure that we never exceed the load of the point of common coupling at the grid, and we can manage the optimized charging to save costs. So either when we have enough PV to charge the battery or the cars, when the tariffs are low to charge the cars faster, when tariffs are expensive, that when there's less sun coming in, that we actually reduce the charging of the cars if that's compliant with the schedule. We call this a microgrid-enabled smart charging. This is just a small scale but very replicable example of how we can use smart technology, data, to manage those challenges at the grid edge. A second example I've brought is from Finland, and some other Siemens colleagues might have talked in some other sessions about that already. The story is about Cello. That's the biggest shopping center in Finland. The situation is the customer, the owner of the shopping center wanted to reduce cost. He wanted to make the shopping center more sustainable. He wanted to modernize the energy infrastructure and also future-proof, integrate already the infrastructure to charge e-cars. The solution we came up with is, on the one hand, we have looked into energy efficiency. So we have made this one of the most energy efficient shopping centers in the world. On the other hand, then we also started to look what else we can do through local generation, distributed generation. So we have installed 600 kilowatts of PV and a medium-sized battery to optimize the local generation and consumption. But then the customer really challenged us and said, this is not enough. He wants to have more value from the assets that he puts into the building. So we have looked into what other values we could find in the building, and we saw that most of the assets in the shopping center are actually not utilized most of the time. Pumps, lighting are never or rarely operating at their maximum capacity. The battery storage is idling around most of the time. So what we've done is we've looked into all of those little margins in the hundreds and thousands of individual assets, and we have collected those flexibilities and pooled them into a virtual power plant. So what we've done is we have set up this virtual power plant and helped the customer to monetize the flexibility, to utilize his assets, and this actually helps the customer to earn 480,000 euros of revenue a year, compared to the on-site benefit through the savings of 118,000. So the ratio is 4 to 1 of value generated for the customer for on-site benefits compared to the monetization of flexibility. So in other words, we've helped the customer to transform the shopping center into a very sustainable, very cost-efficient and a building, but moreover, the building can now be used to stabilize the network. It is an asset that can be utilized to manage the transition of the decarbonized energy system. The third example I've brought is from South Africa. It's a Siemens campus in Midrand, South Africa. The situation there is slightly different. They have an insecure infeed from the utility. That means power outages every now and then, brownouts, challenges in power quality. The second challenge is the high fluctuation of energy cost. Number one, from the energy cost itself. Number two, also from the uncertainty because of the local currency. And the third one is they wanted to change their operating system from a labor-based maintenance and operating system to an analytics-based operating system in order to save cost and labor hour. Labor is very expensive in South Africa. The solution we came up with is we installed a microgrid installing 1 megawatt of ground-mounted PV, 140 kilowatt-hour battery storage system. We have connected the existing diesel generators, and we have connected the newly installed charging infrastructure. What's new with this example is we've also then connected the building management system and the meter data management system. So we're combining the supply and the demand at the local energy system, collecting all the data in our IoT platform. Number one, that helps to provide all the data to actually optimize the maintenance of the site, dispatch technicians when it's needed, but not when it's not needed. On the other hand, what we also now do is we not only manage the optimal mix of generation. When there's sun, we feed in as much as PV as we can, store it in the battery. When there's clouds coming up, we're getting the system, the diesel engine ready to stabilize the system. Secondly, we can if there's a grid outage, we completely disconnect and island the whole site and maintain operations. And as the third element, we can now also combine and optimize the supply and demand side. So when electricity is cheap, we can actually increase the rate the air conditioning is running, for example, and also use then the building almost as a storage element of the system. So holistically optimize the supply and demand side of the overall system. So what we see looking into the future is an increased necessity for our customers, for former energy consumers, owners of shopping centers, industries, office buildings, an increased necessity to take care of their own security of supply. Secondly, an increased focus on reducing energy costs. As energy costs increase, they get a higher and higher share of the actual balance sheet of the OPEX budget of customers. And thirdly, with the increased push to decarbonize locally, and also as for corporate customers. A fourth element that we see is the increased necessity also, or the increased awareness to integrate the new elements of the infrastructure like e-mobility and electric heating. So all of that leads what I always call to a renaissance of microgrids. Microgrids originally come from applications of islands, that's where the name comes from, of microgrids self-sustaining itself, to niche applications and critical infrastructure with a critical requirement to island. Now moving into a massive application at the grid edge, helping to integrate the new elements of the grid edge in buildings, in infrastructure, right where supply and demand meet. How we see that happening is actually, on the one hand, utilizing or using a local control, a microgrid controller, to provide mission-critical control functionality, like managing power quality or the ability to island, but then a digital layer where we utilize the data, apply smart analytics, and then provide value-added services. It's the combination of the local fail-safe hardware and the power of software that will help us to make the energy system of the future efficient and stable and affordable going forward. So, to sum it up, we see new customer value that's being created right where supply and demand meet at the grid edge. And this grid edge leads to a renaissance of microgrid, going from the niche applications into mainstream, allowing to make the solutions of the grid edge smarter. And for us, it's the combination of local fail-safe hardware that provides the resilience but then also the power of software to provide value-added services that enables the energy system of the future. Thank you very much.
Thank you. Any hot question? Alf will not be in the panel. He will have to leave after the session here. I would like to ask you a question about what's your estimate of the number of microgrids projects in Europe, but maybe I saw you have one of the projects in South Africa. So how many microgrids projects we have in South Africa? And second is, have you tested the usage of some new technologies like blockchain for these microgrids, and what could be the benefits?
Yes. On the first question, you mean today or going into the future?
The future.
So today we see kind of thousands of projects, but we see at the grid edge traditionally...
So this is the potential, is to run really thousands of projects in Europe.
That's
in Europe.
Globally, thousands, I would say, like 3,000 or 4,000 is I think what Navigant has quoted in their study recently. I see microgrid in the less loose definition. It's not island, but really providing local fail-safe controls plus the software layer being a standard element if we're talking about managing integration of e-mobility in dense urban areas. So I see that is going into mainstream is what I meant. So if you want to name me down a number, I would say millions. Yeah. And the second question?
Blockchain, yeah.
Blockchain, yes. I mean, I was just touching on that. Actually, we're using blockchain today already. We're using AI. We're using machine learning. That is all part of the cloud layer. So that's the incredible power of software. Once you have access to the data and can send set points and exchange information and control, you can apply all sorts of non-trivial algorithms. So we're playing around with blockchain. We've got 3 pilot projects currently live, one in Germany, one in Austria, one in the US, where we play around with blockchain either for managing certificate of origin or also for energy exchange platforms, market interaction platforms that autonomously exchange and manage energy flows in complex energy systems.
Okay. So the cloud where you have the energy IP and this box at the top right,
exactly.
Right? Okay.
Well, that's kind of the platform.
System.
Exactly, and that's an open API system. And on top of that, that's kind of your application layer. On top of that, we're running all sorts of application.
Okay. Thank you. Thanks a lot.